Good morning, girls. Now, children, in real numbers, we are going to study what is this revisiting rational numbers and the decimal expansion. You know what are rational numbers and how do we find the decimal expansion of any rational number. Okay. Now, based on in this topic, we have three theorems, and based on that, we have exercise 1.4. Okay. Now, see. We are studying real numbers. Any rational number can be expressed in the form of p by q, in which q is not equal to 0 and p and q have no common factor between them. Now, when we find the decimal expansion of any rational number, there are two conditions. The first condition is that it is either terminating, that means that division will stop. After performing some steps, that division will stop, or it will be non-terminating repeating decimal expansion. Okay, I repeat, rational numbers can be we can find the decimal expansion of rational numbers when two conditions arise: terminating and non-terminating repeating decimal. Now, the first theorem, there are three theorems here. Okay, under these theorems, the first one is it says that suppose x is any rational number, okay, whose decimal expansion terminates. The statement is given in your book. I am explaining you in simple words that suppose x is a rational number whose decimal expansion terminates. Now, if x is a rational number, we can write it in the form of p by q. Yes, p and q, as I told you here also, that they have no common factor between them other than 1. So we can write p and q are coprime if the factorization of q, that is this denominator, is in the form of 2 to the power of n into 5 to the power of m, or 2 to the power of m into 5 to the power of n, where m and n are non-negative integers. Okay, I repeat. Theorem 1.5 says that if x is any rational number, we know that whose decimal expansion terminates. Okay, now you know that x can be written in the form of p by q. P and q are coprime numbers. So therefore, if this x is the decimal expansion terminates, then in p by q, q can be expressed in the form of 2 to the power of n into 5 to the power of m, and m and n are non-negative integers. This is only possible when x is whose decimal expansion is terminating. Did you follow what I said? Now, let us read the statement. Let x be any rational number whose decimal expansion terminates, then x can be expressed in the form of p by q, where p and q will be coprime numbers, and the prime factorization of q will be in the form of 2 to the power of n and 5 to the power of m. Okay, and m and n are non-negative integers. This is theorem 1.5. Okay, now the converse of it, that is, converse means the reverse opposite of it. Theorem 1.6. Okay, you read the statement and you will understand it, and then explain you again in simple words. Let x be p by q, it be a rational number such that the prime factorization of q is in the form of 2 to the power of n into 5 to the power of n m, where n and m are non-negative integers, then the decimal expansion of x will terminate. Okay, did you follow what I said? These two statements are converse of each other, that if x is in the form of p by q, where p and q are co-prime, yes, then what will happen? The decimal expansion will be terminating when q can be written in the form of 2 to the power of n into 5 to the power of m. Okay? In simple words, now go back to the previous one. If x is any rational number, okay, and can be expressed in the form of p by q, where q has a factorization of 2 to the power of n and 5 to the power of m, where m and n are negative integers, thus the decimal expansion will be terminating. Okay, when it is terminating, then this condition arises. When this condition arises, then the decimal expansion will be terminating. They are reverse of each other. Okay, now as I told you that, now third one, as I told you that the rational number decimal expansion can be either terminating or it can be non-terminating, repeating. So the third theorem will be theorem 1.7. Okay, now what does this say? See, let x be p by q, be a rational number, such that the prime factorization of q is not in the form of 2 to the power of n and 5 to the power of m. M and n are non-negative integers. Then x, the decimal expansion of x is not terminating, but it is non-terminating, repeating. Okay, so the statement will be, suppose x can be written in the form of p by q. You know that q is not equal to 0, then p and q are what? They are co-prime. Now if q cannot be written in the form of what? 2 to the power of n into 5 to the power of m. N and m are what? Non-negative integers. Thus, the decimal expansion of p by q will not be terminating. It will be what? Non-terminating, repeating. When any term is repeating, children, what term we use for that? Recurring. Okay, so I hope the theorems are clear to you, that if x is any rational number, we can represent it in the form of p by q. P and q will be co-prime numbers. Then the factorization of q will be in the form of 2 raised to the power of n, 5 raised to the power of m. Similarly, when we go to the reverse of it, that if x is in the form of p by q, then the decimal expansion will be terminating only when q can be expressed in the form of 2 to the power of n into 5 to the power of m. Okay, and the third theorem is that if x is a rational number, okay, p by q is the form, it will be non-terminating only when q cannot be expressed in the form of 2 to the power of n and 5 to the power of m. Okay, now in this exercise 1.4, you don't have to divide, you only have to express the denominator in the form of 2 and 5. If it exists, it is terminating. If it doesn't exist, it is non-terminating. So suppose I take first exercise 1.4, question number 1. I'll take the second part, 17 by 8. Okay, now a 17 by 8, it is easy, children. You know that 8 can be written as 2 into 2 into 2, which I can write it as 2 to the power of 3 into 5 to the power of 0. Now can we write this in the form of 2 and 5? So you will write yes. Okay, we can check the answer at the back. It will be we can write 2 to the power of 3 into 5 to the power of 0. So therefore the answer will be terminating. Yes, the only factors which should be present in the denominator should be 2 and 5. Now since over here we don't have 5, but we can write it in the form of 5 to the power of 0, hence it is terminating. If there are some other factors, then it will be non-terminating, like fifth one, 29 upon 343. Now what do you say about 343? Now 343 can be written in the form of 7 into 7 into 7. Okay. Now therefore we have factors here, 7 cube. We can write 2 to the power of 0, 5 to the power of 0, but we have this here. Now therefore what do we conclude? That therefore therefore we'll write 29 upon 343 is the decimal expansion of 29 upon 343 is non-terminating, repeating. So as I told you that you don't have to actually divide, you just have to write terminating or non-terminating. Now as you can see questions here, children, 3125. If we check about for this 13 upon first one, 13 upon 3125. 3125 you can factorize and write 5 6 are 30, 5 2s are 10, 5 5s are 5 1s are 5, 5 2s are 10. All the factors, okay, they are just 5. So we can write 13 upon 3125 is equal to 13 upon 2 to the power of 0 into 1 2 3 4 5, 5 to the power of 5. So for this what will you write? It will be terminating. Yes. So I hope you can complete this exercise. Like over here, 455, find the factors. You will come to know whether it is terminating or it is not terminating. So for today what you do, you write these 3 theorems in your notebook and learn these statements. It is easy to learn as I have explained you in simple words. Then try this exercise, question number 1. Complete this today. Tomorrow I'll continue the next, that is 2 and 3. Today this is the set of questions which you have to complete. Okay. Any doubt if you have, you can ask me. Even if you have any previous doubts, you can ask me, children. Okay. Thank you. Have a good day.